My name is Thorsten Sattler, and this is joint work with Thomas Schöps, Victor Larsson, and Mark Polyface on why having 10,000 parameters in a camera model is better than 12. In this work, we consider the problem of highly accurate camera calibration, which is an important prerequisite for 3D computer vision applications such as structure for motion and stereo. The goal of the calibration process is to associate each pixel with the corresponding viewing ray in 3D. Traditionally, parametric models are used. They model the mapping from pixels to rays through only a few parameters corresponding to physical attributes, such as the focal length. Parametric models have been used successfully for decades. But how accurately do they actually model the camera geometry? To answer this question, we visualize reprojection error directions. Ideally, we would like to see a random pattern. In practice, however, we observe regions with similar directions, indicating biases in the calibration. Due to their small number of parameters, traditional parametric models do not accurately model the relation between pixels and viewing rays. Generic camera models define the mapping from pixels to rays on a per pixel level, without any physical interpretation of the camera geometry. They allow for completely independent rays for each pixel. However, in practice it is common to assume that the viewing rays vary smoothly and use this for regularization. The model shown here is a central model, with all viewing rays intersecting in a single center of projection. However, non-central models are also possible. The number of parameters in both central and non-central models is roughly linear in the number of pixels. In this paper, we propose a calibration procedure designed for highly accurate camera calibration. We use a custom calibration pattern for data capture. Compared to a standard checkerboard pattern, the Siemens star-like design leads to more accurate feature detections. We extract features at the center of the pattern elements. To obtain highly accurate detections, we exploit mirror symmetries around the pattern for refinement. We initialize the parameters for either a central or a non-central model using the approach from Ramalingam and Sturm. Rather than modeling each pixel, we use a set of control points. For each control point, we store a ray or line and use interpolation on B-spline surfaces to obtain the rays for the remaining pixels. Finally, we use bundle adjustment to refine the camera model as well as the pattern geometry to account for non-planarities. Next, we compare generic calibrations obtained with our pipeline to traditional parametric models. This is the same visualization of the reprojection error directions that I showed earlier. Here we use the thin prism model with 12 parameters to calibrate the color camera of an RGB-D sensor. This is a calibration for the same camera that we obtained with OpenCV's model, which also has 12 parameters. There is a clear bias for certain viewing directions, indicating that the model does not fit the camera geometry well in those regions. Switching to a central model with about 5,000 parameters significantly reduces the bias, even though we are still able to observe patterns in the error directions. Increasing the number of parameters to 10,000 improves calibration accuracy. We obtain the best results with a non-central model with around 26,000 parameters, resulting in a nearly random distribution of error directions. A natural question is whether the bias has an impact on applications. To answer this question, we conducted a structure for motion experiment. Since no ground truth is available, we compare the drift between the trajectories obtained with a generic camera model and a parametric model. In this case, we observe a drift of about 2% over the length of the trajectory. This is significant as state-of-the-art SLAM systems typically exhibit a drift of 1% or less. Naturally, the improvement depends on how well the parametric model is able to describe the camera geometry in the first place. In summary, this paper presents an improved calibration pipeline for generic models and shows experimentally that such models reduce bias in calibrations and improve performance in practice. At the same time, there's little to no runtime overhead when using central models. We believe that generic models should be used more often in practice. To facilitate this, we make our source code publicly available.